Okay. Good morning, everyone. Welcome to Home Institute. So sorry, I was late. There's a problem with the setup. That's why session was delayed a bit. So without wasting the time, so I'll start the session. Okay. So yeah. Good morning, Venkat. Good morning, Rohan Singh. Dinesh, good morning. Okay. I'm Giri, faculty of Home Institute for Power System subject. So in this marathon session, first we will see the power system 1. The power system 1 deals with the T&D part, the transmission and distribution part. So in this session, initially we will discuss the formulas and the important concepts, and later we'll solve the numerical questions to understand the concepts in a better way. Okay, clear? So T&D, if you see, the very important topics in T&D, if you notice, the line parameter calculation and performance of transmission line, voltage control, and also the insulators, cables and distribution systems. But very important topics are line parameter calculations, performance of transmission lines, and power factor correction, voltage control. If there is a question in GATE exam, means generally 90% probability that the question will come from these areas. Okay, clear? So first we'll start with the line parameter calculation. So our first topic is line parameter calculation. Line parameter calculation is our first topic. Okay. So the first important thing is the calculation of resistance, calculation of inductance and calculation of capacitance. See, line has 4 parameters. The transmission line we represent using 4 parameters here. So if you have a transmission line between sending end and receiving end, suppose if you have a line between sending end and receiving end, it is represented using 4 parameters, the equivalent circuit. There is a resistance, there is an inductance, in the shunt branches there is a capacitance and a conductance. These are the 4 parameters every transmission line has. Truly speaking, these parameters are what? Lumped parameters or distributed parameters. If I write like this, this is a lumped model. But in practice, these transmission line parameters are distributed in nature. Means what? If you cut the transmission line into n number of sections of equal parts, every little part you take it, in that there is a resistance, there is an inductance, there is a capacitance and what? Conductance. So that means the transmission line parameters are what? Distributed in nature. Okay, clear? So that's why when it comes to the analysis, performance analysis, see, when it comes to long transmission lines, we generally take what? Distributed parameter model. But short and medium lines, so for better approximations, we go with what? The lumped parameter model only. So these are the 4 parameters we have. But what is the resistance? Resistance is directly simple, R equal to rho L by A, where rho is the resistivity, L is the length of the line, A is the cross section area of the conductor. So this is the simple formula to calculate the resistance, but this is what? Careful, the DC resistance. But if you see AC resistance, because this is the line we are using to carry the power, AC power, better to say, AC current, okay, AC power. So RAC is approximately 1.6 times what? RDC. Okay, why this 1.6 factor came? This is just to account for what? Skin effect. Okay, this is the first important thing you need to notice for resistance calculation. AC resistance is generally greater than what? DC resistance. Okay, So that's about resistance calculation, nothing great. Okay. Now, if you want to calculate the inductance, okay, for inductance calculation, if you see, the generalized formula for inductance calculation is this: 2 into 10 power minus 7 ln of GMD by GMR. This is a shortcut formula for inductance. This is the inductance. We can use it for what? Single phase line and three phase line. For any given configuration, if you are able to calculate the GMD and GMR, we can easily substitute here and we can get the answer. 2 into 10 power minus 7 ln GMD by GMR. Okay, clear? Suppose if you see single phase transmission line. Single phase transmission line means what? We have two conductors. They are separated by a distance called D. This conductor is A, let's say this conductor is B. Now this conductor is carrying a current of IA, this conductor is carrying a current of IB. You know that IA equal to, let's say, I, then IB equal to what? Minus I, because one conductor is what? Go conductor, and other conductor is the return conductor. One conductor we say phase conductor, other conductor we say neutral conductor. You know already these things. Yeah. So for this single phase transmission line, the inductance is, we can write the L single phase first. L single phase. Directly I am giving the formula here. 2 into 10 power minus 7 ln D by R dash Henry per meter. Where R dash we can write e power minus 1 by 4 R, which accounts for internal flux linkage. E power minus 1 by 4 R, otherwise 0.7788 times R. Okay, clear? Now, if you notice, the single phase circuit inductance, L circuit, sometimes he will ask you what is the circuit inductance or total inductance or loop inductance, means which is what? 2 times L single phase. 2 times L single phase. Okay. So this is under the assumption of the radius of the conductors R1 and R2 are what? Same. If the radius of the conductors is different, again the formula will change, because we have to calculate LA separately. If the radius is not equal, R1 not equal to R2, then what? We can calculate like this, LA separately. What is that? 2 into 10 power minus 7 ln D by R1 dash Henry per meter. LB separately, 2 into 10 power minus 7 ln D by R2 dash Henry per meter. Now, what is L single phase? That is nothing but what? L average, which is LA plus LB by 2. What is L circuit? That is LA plus LB, circuit inductance, LA plus LB. Now these are the formulas which are very, very important, when we are dealing with single phase transmission line. Clear? And one more important thing is that, okay, this is without considering mu r value. Sometimes the mu r value might be given in the problem. Till now there is no question in the GATE history or in IES and even what, the other competitive exams. Till now this kind of question is not given. That means by giving mu r value of a conductor. Suppose if the mu r value is given, how to handle? It's very simple. If the mu r value given, no, let's see. We'll go to the next slide. Suppose if mu r is given, if mu r is given, then we have to go like this. Ln of 1 by R dash, otherwise D by R dash, let it be, can be replaced with what? mu r by 4, remember this, plus ln d by r. You can replace. Even you can remember this also. Ln of 1 by r dash can be replaced with what? 1 by 4 plus ln 1 by r. If you come across mu r value, you can replace like this. So we'll solve a problem so that you will get a clarity on this. Okay? But remember, if mu r value given, then this is the replacement. Okay? So ln 1 by r dash can be replaced with 1 by r plus what? Sorry, mu r by 4. Yeah, mu r by 4 plus ln 1 by r. Otherwise, ln d by r dash can be replaced with what? Mu r by 4 plus ln d by r. Okay? Clear? So these are the two important things you should notice if mu r value given. Okay? Remember these formulas. This will definitely help you while solving the questions. We'll solve a question here so that you'll get a clarity on, so how to handle the problem, okay, if mu r value given and if the question is asking about L single phase, L circuit, etc., etc., etc. So let's take up a problem here. Yeah, there are few doubts asked. Is power system about to complete in one session? Yes, I will try to complete in one session. That is T&D part. Most probably one more session I will take for analysis. Okay, we'll see how it will goes. Yeah, I will share these slides. Don't need to worry. In our Telegram channel. So I will share these slides. Okay. Okay. Now we'll solve an example here. So let us see an example. Possible I will change the background. Okay. A single phase transmission line has two conductors. Radius 1 centimeter and 2 centimeter respectively. Spacing between them is 2 meters. The first part of the question, mu r equal to, let's say, 5. Calculate inductance of single phase transmission line. This is how the question is given. Inductance of single phase circuit. Inductance of single phase circuit. Now, the second part of the question. If mu r equal to, let's say, 1, calculate inductance of single phase transmission line. Calculate inductance of single phase circuit. See, this is the question. So there are two conductors. Just see here. The radius is what? One conductor is what? 1 centimeter, and second conductor is what? Radius of 2 centimeters. Okay. Now he is asking to calculate the inductance of single phase circuit and single phase transmission line. Let's try to do this. Try to solve this. Okay. Right. I hope you are solving this. But anyway, let's see. There are two conductors, right? The conductors one radius is two conductors given. They are separated by a distance called 2 meters. Conductor 1 radius R1, let's say, that is this is a conductor 1, let's say this is a conductor 2. Otherwise A conductor and B conductor, better to write like this. Okay, R1 is given 1 centimeter, which is 0.01 meter. Careful sir, we have to convert into meters here, and sometimes instead of radius diameter is given. This is a common mistake done by the people in the GATE exam tomorrow. If the same question is given, this is the mistake done by the people. They will, maybe radius diameter is given, but they will take it as radius, okay, and they will solve the problem. Okay, the stress will be like this in the GATE exam. You are unable to read properly the question. The diameter is given or radius is given, but by default we take it out radius, because most of the questions we solve with radius is given. Suddenly if diameter is given but we consider as radius, that's it, we end up with wrong answer. If diameter is given, what do? You have to make it off. Okay, now tell me, this is 1 centimeter and R2 is what? 2 centimeters, means 0.02 meters. Okay, now see the first question, first part of the question will solve with what? Mu r equal to what? 5, and radius also not same. That's why what you have to do, you have to calculate LA separately, LB separately. Careful about this. If radius is what? Same, directly you can do it, but if the radius is not same, LA you have to calculate separately, LB you have to calculate separately. Okay, so I'm going to calculate LA separately. What is LA formula? 2 into 10 power minus 7. Yes, ln d by RA dash or R1 dash. This is Henry per meter, no? Now if you want, I can write a 0.2 ln d by R1 dash. That is what? Yeah, 0.2 ln d by R1 dash. This is in what? Millihenry per kilometer. Most of the time the answer will be generally given in millihenry per kilometer. Okay, so 10 power minus 6 I taken out, I written as millihenry per kilometer. Okay, both are okay, right sir? So 0.2, yeah, I'm going to write now LA. What is LA? Yeah, I'll write here 0.2 ln 0.2 times mu r by 4 ln d by r1 dash. I am writing like this, mu r by 4 plus ln d by r1. See, indirectly, this is what? The inductance due to internal flux linkage. This inductance due to internal flux linkage. This is what? Inductance due to external flux linkage. Inductance due to external flux linkage having two terms. One is, the mutual inductance part, that is because of D, and self-inductance part, that is because of R1. I'm going to write now, later, no need to worry. Okay, clear? So, this is what? The inductance due to internal flux linkage. Mu r value is going to affect the inductance due to internal flux linkage, but it is not going to affect the inductance due to external flux linkage. Okay, so if mu r value increases, what happens? Self-inductance will increase. You may also say the inductance due to internal flux linkage will increase, if you are more specific. Again, self-inductance having two parts. I'm going to write at the end that formula. Okay, clear? So now what is the answer here? 0.2 ln, yeah, 0.2 mu r by 4. Mu r is what? 5 by 4 plus ln d is what? 2 by 0.01, the first conductor radius. So let's try to solve this. Okay, what do you get? Ln 200 here plus 1.309 millihenry per kilometer. Now similarly, what is LB? LB, if you want to calculate, tell me. Directly I am writing the formula, 0.2 times mu r by 4 plus ln d by r2. So how to write this? 0.2, what is mu r? Ln d is what? 2 by 0.02 millihenry per kilometer directly. Chalo, what is the final answer here? Ln 100 plus 1.25 into 0.2 will get 1.171. See, 1.171 millihenry per kilometer. So that is the LA and LB, but he's not asking LA and LB. He's asking what is the inductance of single phase transmission line. If it is single phase transmission line means what? Single phase transmission line, L single phase. How to write? L average. L single phase, L average, both are what? Same. Average inductance. LA plus LB by what? 2. This is what the average inductance. Okay. Let's calculate the average inductance here. What I get? So 1.309 plus 1.171 divide with 2. So you get approximately 1.24 millihenry per kilometer. Now if that is the case, what is the B part of the question? B part of the question is what? L circuit. What is circuit inductance? Nothing wrong to write like this, LA plus LB. What is LA plus LB? 2 times L single phase, no? You can write like that also. 2 times L single phase also. That is also correct, right? So if you solve this, what I get? .48. Clear? Now, the next question, if you see, the second part of the question, he has given what? Mu r equal to 1. You can try, if mu r equal to 1, what do you get? Okay. Yes, 1.24 is correct. Sajan, yes, I'm going to solve some previous year questions also. Sajan, how it becomes 2 times L single phase? Because see, circuit inductance is what? It's a 2 conductors, no? Single phase transmission line has 2 conductors. Circuit means what? LA plus LB. LA plus LB. This is A conductor and B conductor. And here is your load. Circuit means what? This is called circuit. LA plus LB we have to do. LA plus LB is the circuit. Now tell me, what is LA plus LB? Okay, here you see LA plus LB by 2. So LA plus LB you can write what? 2 times L single phase. Yes or not? Directly I written here. Okay. Clear? I hope this is clear for you. Right. Now we'll go to the next part of the question. If mu r equal to 1, then how to solve? Again, what is LA? 0.2, 1 by 4, ln d by r1. The dash will not come. You can also say this is what? 0.05 plus what? 0.2 ln d by r1. Okay. Somebody raised a doubt on this. This is the answer. Okay. You can use any formula, ma. You'll get the answer. This formula also, okay, fine. But this is what? LA and R1 we got. Then if you substitute here, what do you get? 0.05 plus 0.2 in millihenry per kilometer only, this one. Yes, 0.2 ln, tell me, d by R1. D is what? 2 meters. R1 is what? 0.01. So what do you get? .1096. Now what about LB? Mu r is what? 1. That's why I substituting here directly 1. Okay, I hope you understand this. So what do you get if you solve this? What is D? .971 millihenry per kilometer. Now, again, what is L single phase? LA plus LB by 2. If I solve this, what I get? It's approximately 1.04. Now, what about L circuit? That is LA plus LB, which is what? 2 times L single phase, nothing wrong. So, what do you get now? 2.08. Earlier 2.48, now 2.08. So, if mu r value increases, what is the conclusion? Mu r is 1, 2.08. Mu r is what? 5, 2.48. So, if mu r increases, now the inductance increases. Inductance of single phase line or 3-phase line, which will always increases. I hope you understand this. Okay, clear? Now, so the next important thing is, as I mentioned, no, the inductance means what? It has 3 parts. So inductance I can write like this. Okay, just like for single phase line, 2 into 10 power minus 7 ln d by r dash. This is a formula if there is no, under the assumption, this formula is what? Under the assumption of what? Mu r equal to 1 and r1 equal to r2 equal to what? R. Then only this is true, otherwise no. Correct or not? Otherwise, if r1 not equal to r2, if mu r is given, try to solve LA separately and LB separately. Okay, if r1 equal to r2, now LA and LB are same. Yes or not? Single phase transmission line, 2 conductors A and B. What I can write now? If r1 equal to r2, this implies LA equal to what? LB, no doubt. LA equal to LB. Okay. So what is the formula in that case? 2 into 10 power minus 7 ln d by r dash. Okay, if r1 equal to r2 and mu r not equal to 1, then in that case what you have to do? LA equal to LB, you have to solve like this. 2 into 10 power minus 7 fine, but ln d by r1 dash, r dash is there, no, that you can write like this. Mu r by 4 plus ln d by r. Ln d by r, you have to write like this. Okay, so if r1 not equal to r2, then what? You have to separately calculate LA and what? LB using the procedure. Okay, if you want, I will write that also. A and B, if R1 not equal to R2, R1 not equal to R2, for example, then mu r equal to 1, then LA formula 2 into 10 power minus 7 ln d by r1 dash. LB formula is what? 2 into 10 power minus 7 ln d by r2 dash. Yes or not? Clear? For example, R1 not equal to R2 and mu r also not equal to 1. In that case, LA separately what? 2 into 10 power minus 7. As I mentioned, no? Yes, this can be written as what? Mu r by 4 plus ln d by r1. Now dash will not come, d by r1. I have noticed this. Again, if you substitute, dash gone. LB means what? Careful about these formulas. These are very, 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 very important. Okay, clear? Just have a look of them. These formulas really important. I hope this is clear for you. Okay, now apart from this, as I mentioned, what is the three parts of the inductance? Let's see. Now, okay, again I am taking single phase line only, assuming mu r equal to 1, assuming R1 equal to R2 equal to R. Then what is the formula for LA equal to what? LB. That is equal to what? 2 into 10 power minus 7 ln d by what? R dash. Yes or not? Let's see, I can write like this now. 2 into 10 power minus 7. Mu r is 1 by 4 plus ln d by r. Yes or not? Again, further I can modify like this. 2 into 10 power minus 7. Okay, let me write in, this is in Henry per meter, right? This is also Henry per meter. So if you want this, if you want this in millihenry per kilometer, then what I do, put here 0.2. 1 by 4 separately plus ln d by r I am writing like this. Ln 1 by r minus ln 1 by d. This is what millihenry per kilometer, because I took here 0.2 instead of 2 into 10 power minus 7. You should hold this procedure. This is very, very important. Okay, now tell me. I get here 0.05 plus 0.2 ln 1 by r minus 0.2 ln 1 by d. Now, this is what, okay, let me write here. Three parts, no? As I mentioned. This is the inductance due to internal flux linkage. I'll use another color pen. Yes. This is what inductance due to internal flux linkage. Inductance due to internal flux linkage. Now this is what inductance due to external flux linkage. Now this is what we call mutual inductance. Mutual inductance. Inductance due to internal flux linkage, inductance due to external flux linkage, and this is called mutual inductance. Now together these two terms is called self-inductance. So what is LA equal to what? LB? LS minus what? LM. Self-inductance minus what? Mutual inductance. What is L in single phase? Also you can write like this. LS minus what? LM. Self-inductance minus what? Mutual inductance. That is the formula. But the self-inductance having two parts. The inductance due to internal flux linkage and what? Inductance due to external flux linkage. So, now this is always independent on the size of the conductor. Always constant. Constant and independent on size of the conductor. But L external depends on what? Size of the conductor. It depends on size of the conductor. But mutual inductance depends on what? Spacing between the conductors. Careful. Mutual inductance depends on spacing between the conductors. Self-inductance depends on size of the conductor. Yes, self-inductance having two parts. Inductance due to internal flux linkage, yes, that is independent on size of the conductor, independent on even spacing between the conductors also. Independent on size of the conductor and spacing between the conductors. Yeah, let me write here, and spacing between the conductors. I hope this is clear for you. But the mutual inductance is what? Depends on spacing between the conductors. Clear? So self-inductance having two parts, internal flux linkage and external flux linkage. Okay, we'll solve a question on calculation of self-inductance separately and what? Mutual inductance separately. Okay, clear? Now again, so I'm just considering here a single phase transmission line. Let's take an example. Okay, a single phase transmission line is given. The spacing between them is what? Assume 1 meter. Diameter of both the conductors are what? Given. And it is 3 centimeters, for example. Okay, now the question is what? What is self-inductance and what mutual inductance? If mu r value mentioned, not mentioned. If mu r value not given, take it as 1 always. Okay, now what is the solution here? It's very simple. Let's have a look. Yeah, self-inductance means what? LS, I can write like this. 2 into 10 power minus 7 ln, d will not come, ln 1 by r dash. Mutual inductance means ln 1 by d. Okay, even you can write like this. 1 by r dash we can replace like this now. Okay, 0.2 to get millihenry per kilometers. 0.2, tell me. 1 by 4 plus what? Ln 1 by r. This is also correct. You can replace. If you want, you can write like this. Nothing wrong. Because if you write like this, this is what? Okay, let me write 0.05 plus ln 1 by r. Now this is what? Inductance due to what? Internal flux linkage. If mu r is there, here mu r will come. Now this is what? The inductance due to what? External flux linkage. Now both are together, we say it is a self-inductance. Now tell me what is the self-inductance here? 0.05 plus ln. Yeah, diameter is given 3 centimeter. But what is the radius of two conductors? R1 equal to R2 equal to R. That is 1.5 centimeters. In meters, 0.015 meters. Let's substitute here. Always you substitute in meters, not in centimeters. 0.015. So what is the answer? Right. Now similarly, mutual inductance I am writing here. 0.2 ln 1 by spacing between them is what? Let's consider the spacing between them is 2 meters here. Better. You'll get the minus answer, no need to worry. Have you noticed? No? This is in Henry per meter, this is in millihenry per kilometer. Now, solve these two. So the mutual inductance is minus 0.138629. Now the self inductance is రాట్లేవరా నువ్వు ఒకసారి రైట్ రా. Okay students, we'll start now. Hello. Yeah. So that's about single phase transmission line. Now we'll start a three phase transmission line. Okay. So in case of a three phase transmission line, you know, now we'll see inductance of three phase transmission line. So there is a one thing you should be very careful with the three phase transmission line. The transmission line might be transposed or it might be untransposed. Okay, what is called untransposed line? Between sending end and receiving end, the conductors are located like this: A phase, B phase and C phase. This is called untransposed line. Three phase line. Now what about transposed transmission line? The transposed transmission line means, yeah, the conductors are what? Connected like this. They are exchanging the positions. Now this is what we call transposed transmission line. The exchanging of positions is done for every 1/3 of the length. See, because of this transposition, I'm going to quickly review what happens. Without transposition, no, the self-inductance of all the phases are same. But mutual inductance of all the phases are not same here. And even we get an unbalanced inductances, and there exists what? Communication line interference. But because of transposition, average inductance will remain same, but the inductances become what? Equal in all phases. Self-inductance anyway same, mutual inductance also becomes same now. Mutual inductance become real values, earlier complex values. I'm not going into the derivation, I'm directly saying. And even because of transposition, the main advantage, the communication interference is what? Nullified for both symmetrical and unsymmetrical configuration. Okay. So by default, we are going to see now transposed transmission line. If it is not mentioned, by default it is what? Transposed transmission line only. Okay. So now we'll see different configurations here, the formulas for the inductance, right? Chalo. Just hold on. Okay, now I'll go to the next slide. Yeah, have a look here. Yeah. So first, as I mentioned, we are going to see here, if it is a symmetrical configuration. First we'll see unsymmetrical configuration. What is the inductance per phase? Unsymmetrical configuration. The formula for inductance per phase is this. The formula for inductance per phase is inductance per phase, you may say, or you may say L average, both are same, that is equal to 2 into 10 power minus 7 ln of cube root of xyz by r dash, which is Henry per meter. Clear? See, this is what the configuration, 3 conductors, same radius. Conductor A, conductor B and conductor C, this is x, y, z. X is the distance from A to B, y is the distance from B to C, and C is the distance from, Z is the distance from what? C to A. If that is the case, we can use this formula, cube root of xyz by r dash. This is for what? Unsymmetrical configuration. For symmetrical configuration, symmetrical configuration is also called equilateral spacing. symmetrical configuration, if you notice, it is also called equilateral spacing. It is also called, balanced configuration, equilateral spacing, symmetrical configuration, all are same. The conductors are arranged to form an equilateral triangle here, ABC, where x equal to y equal to z, that is equal to d, right? Now the radius of all the conductors is same. In that case, we can write the inductance per phase is simply 2 into 10 power minus 7 ln of cube root of xyz by r dash, right? You substitute x equal to y equal to z equal to d, then you get what? 2 into 10 power minus 7 ln of what? D by r dash. So that means what I want to say here is, if you are able to remember this formula, it's just a matter of what? Substituting x, y, z. You can get the answer for remaining. Next configuration is what? The next configuration is the next configuration I can say horizontal spacing and vertical spacing. For both horizontal and vertical spacing, again the formulas are same. Horizontal spacing and vertical spacing. So for horizontal and vertical spacing, if you see the conductors how they are arranged. So the horizontal spacing means what? The conductors are arranged like this, such that the distance between, let's say, A, B, C conductors here, A to B D, B to C D, and C to A, this is what? 2D, right? Now vertical spacing means what? Something like this. So in this case, for both the cases, x equal to y equal to what? D, z equal to what? 2D, right? Now tell me, what do you get? The inductance per phase. 2 into 10 power minus 7, directly I am writing ln of 2 power 1 by 3 d by what? R dash. Millihenry per kilometer. Now these are the formulas which are very, very important when you are dealing with what? Three-phase transmission line. I hope this is clear for you. Okay, now we'll solve some gate questions on line parameter calculations. Okay, and before that, okay, so this is about the inductance calculation, but when it comes to the capacitance calculation, it's very simple. The inductance and capacitance only one difference. In case of inductance calculation, there exists what? R dash here. Why R dash accounts here? R dash accounts for internal flux linkages. Okay, but there is no concept like internal charge. So that's why for capacitance calculation, if you see the capacitance calculation, quickly I will write the formulas. Capacitance calculation. Yes. Now if you see single phase transmission line first, single phase transmission line, again we can write the capacitance of single phase line and capacitance to neutral of a single phase line. Okay, capacitance of a single phase line and capacitance to neutral of a single phase line. Let's have a look. Capacitance of a single phase transmission line. The formula is what? CAB. You have to write CAB. That is what? Pi epsilon naught ln d by r. You know what is d? Spacing between the conductors is d. The radius of both the conductors I am assuming same. Okay. So that is a formula. Ln d by r. Farad per meter. Careful. Now what about CAN? Capacitance to neutral of a single phase transmission line. If he is asking to calculate what is the capacitance to neutral of a single phase transmission line, then you have to use this formula. So CAN is equal to what? 2 times CAB. Okay, CAN equal to 2 times CAB. Then the formula is 2 pi epsilon naught ln d by r farad per meter. Now we'll ask to calculate the charging current also. What is the charging current? The current drawn by the capacitance is called what? Charging current. Charging current of a single phase transmission line, that is what? V into omega into CAB. Careful. V into omega into CAB. By default, whatever the voltage is given, that is what, the phase voltage only for single phase transmission line. You don't need to worry about what is the phase voltage and line voltage. By default, whatever the voltage is given, that is nothing but what? Phase voltage for single phase transmission line. Yes. Okay. Now have a notice here. Is the R dash came or R is came here? R only. Why? That R dash accounts for internal flux linkage for inductance calculation. But while calculating the capacitance, we use this formula C equal to Q by V. Q by V. There is a internal flux. Internal flux is there for the conductor. For a conductor, always the flux starts from the center. But when it comes to the same conductor, what about the charge? Charge is only accumulated on the surface of the conductor. It might be positively charged or negatively charged. That's why there is no concept like internal charge here. There is no concept like R dash, only R. Okay, clear? So the concept of R will come here, but not R dash. That's it. So the next important thing is that, yeah, for a three-phase transmission line, if you see three-phase transmission line, chalo, if you see three-phase transmission line, the capacitance calculation is that again, quickly we have a what? Symmetrical configuration. I'm not going to draw the configuration. Directly I will write here. Symmetrical configuration. Symmetrical, and before that unsymmetrical. Unsymmetrical configuration. The capacitance per phase is what? 2 pi epsilon naught ln of, I hope you understand now. The logic is simple. Cube root of x by z by r. Earlier what we written 2 into 10 power minus 7, this ln of cube root of x by z by r dash is came in the numerator for inductance, but here what? Denominator. Now unsymmetrical configuration now. Symmetrical configuration. What is the capacitance per phase? We say capacitance per phase for three-phase line 2 pi epsilon naught ln of d by r. horizontal and vertical configuration. Horizontal and vertical configuration. What is capacitance per phase? The units are what? Farad per meter everywhere. Careful about that. There Henry per meter, here what? Farad per meter. Clear? Okay. Now we'll solve some questions. The previous questions only. See this question. Consider an overhead transmission line with 3 conductors shown. DAB, DBC, DC are given equal. Means what? So it is an equilateral spacing. That's what we can understand. Yes. Now what is asking? The resistance of the conductors are neglected. The geometric mean radius GMR is given 0.01 meters. GMR means what? R dash, truly speaking. Okay. If it is GMR, no, that is what by default R dash. We'll discuss the concept of GMR also, no need to worry. But notice one thing, GMR means what? By default R dash. Okay. Is given 0.01 meters. Now what is asking? Neglecting the effect of ground, the magnitude of the positive sequence reactance in ohms per kilometer. Positive sequence reactance means just reactance. What is that? 2π FL, where L is the inductance per phase. Okay, is asking what is that X in ohms per kilometer. Round up to 3 decimal places. Okay, so what is the inductance first? The inductance means what? 2 into 10 power minus 7 ln of d by r dash. Why? It's an equilateral spacing, Henry per meter. Equilateral spacing, 2 into 10 power minus 7 ln d by r dash, Henry per meter. Now otherwise 0.2 ln millihenry per kilometer we get. 0.2 ln d. D is given what? The spacing between the conductors is same, that is what? 1 meter. Okay, 1 by r dash directly given 0.01. So millihenry per kilometer. So 0.2 ln 100, just check it. 0.2 ln 100 is the answer. Check it. So that is 0.921 millihenry per kilometer. 0.2 ln 100 means 0.921 millihenry per kilometer. Okay. But he is not asking that. He is asking the reactance. That is what? 2π into 50 Hz system into 0.921 into 10 power minus 3. If you add like this, so that it will be in ohms now. Ohms, and denominator what? Kilometers. So ohms per kilometer is asking. Okay. Point 28935. So point round off to what? 3 decimal points. That's why the answer is what? 0.289 exactly. 0.289 millihenry per, sorry, ohms per kilometer. The answer is what? 0.289 ohms per kilometer. Check it whether you got the same answer or not. So how can we understand R or R dash? See, very simple. Inductance calculation, everywhere R dash will come. Capacitance calculation, everywhere R will come. That's it. There is no R dash for capacitance calculation. It is just R. Inductance means you have to use what? R dash. Right. Now we'll see the another gate question. Let's try to answer this question. Oh, I'm sorry. I think we took the same question. Just hold on. Yeah, try to answer this question. A single phase transmission line has conductors of each of 10 mm radius. Two conductors having what? 10 mm radius. Okay. These are fixed at a center to center distance of 1 mm, 1 meter in a horizontal plane. This is now converted to a three-phase transmission line by introducing a third conductor of the same radius. This conductor is fixed at an equal distance from the two single-phase conductors. The three-phase line is fully transposed. The positive sequence impedance per phase of three-phase system is to be 5% more than that of the inductance per conductor of the single-phase system. Okay, the positive sequence, not impedance, inductance. I'm sorry. Okay. Yeah. Here it is, the positive sequence, not impedance, inductance. Typing mistake. Yeah, the positive sequence inductance of a three-phase system is what? 5% more than that of what? The inductance per conductor of a single phase system. Inductance per conductor means what? L single phase. See, initially this is what? Single phase transmission line. This is, shall I say, case 1. Initially the two conductors are there. Each conductor having radius of what? 10 mm. 10 mm means what? Just hold on. It's 10 mm. Okay. Yeah. 10 mm. Nothing wrong to say what? 10 by 1000 meters, 0.01 meters. Okay. Now the spacing between them is what? 1 meter. Right. Now what is L single phase here? L single phase means what? See, two conductors, same radius. Now I can use this formula, 2 into 10 power minus 7 ln what? D by R dash, otherwise what? 0.2 ln D by what? R dash. Clear? Millihenry per kilometer. Yes or not? So if we substitute 0.2 ln, what is D? 1 meter. Divide with R dash means what? 0.7788. So what is this value? Just check it. Now case 2, what is done? Now this single phase line converted to three phase line by introducing a third conductor. Where is that third conductor? Having same radius. The radius of this third conductor also 0.01 meters, but which is located at an equidistance D. Now this is what? 1 meter. Okay, clear now? Let's assume this is A, B, C. If that is the case, now tell me x equal to what? D, y equal to D, z equal to what? 1 meter. Clear or not? So what is inductance per phase of three phase line now? 0.2 ln of what? Cube root of xyz by R dash. Let's substitute here 0.2 ln cube root of xyz, cube root of what? D square, D into 1, so D square by R dash 0.7788 into 0.01. This is in millihenry per kilometer. Now tell me, what is mentioned? The inductance per phase is what now? 5% more than of what? And that means what? 1.05 times what? L single phase. So inductance per phase one side, 1.05 times L single phase one side. Then you can get what? The value of D. You can solve for D now. So we get this 0.971 millihenry per kilometer. Similar kind of problem we already solved. Just check it. .971 millihenry per kilometer. Now let's substitute here. We'll go to the next slide. So that means what? Inductance per phase is what now? Shall I write here? 0.2 ln cube root of d square by 0.7788 equal to 1.05 times 0.971. So if you go to the next slide, let me write here like this: ln of what? Cube root of d square by 0.7788 into 0.01, that is equal to 1.05 times 0.971, 0.971, right? Okay. 0.971 by 0.2. The 0.2 will come here. So if you do this, what I get? 5.09775. Okay, now we can write like this: cube root of d square by 0.7788. Both side if you do e power, so e power and ln get cancelled here. Here what? E power 5.09775. So what is this? So if I solve this, 163.653, 163.653. Now tell me what I get here. Cube root of d square equal to this. So you will get something. Now I can write this is what? D power 2 by 3 is this. .2745. Now what is D now? Whole power 3 by 2 now. Which will be 1.438 meters. Now this kind of questions are very, very common in the GATE exam. Okay. It's not a straightforward question, right? See, not 5%, it is 5% more. That is what mentioned in the problem. Mamata, it's not 5% of L single phase. It is mentioned that 5% more. I hope this is clear. 5% more. Okay. Chalo, we'll take a 30 minutes break here for lunch break. Then after the lunch, we'll continue for few more questions on the line parameter calculation, and also we'll solve performance of transmission lines. Exactly 30 minutes break. Okay. Okay, we'll start the session now. Okay, is my voice is clear now? So we'll start the session. So now we'll discuss one more question here. So before that, the calculation of GMR and GMD. We'll see now calculation of GMD and GMR. GMD means geometric mean distance and GMR means geometric mean radius. Now, when we apply the GMD and GMR concept, if the conductors are belongs to same phase, we apply GMR. If the conductors are belongs to different phases, we apply GMD. Okay. For example, we have two conductors. Let's say conductor 1 and conductor 2 and conductor 3. Let's say the name of the conductors 1, 2 and 3. This is what carrying a current I. This is one group, and another conductors, let's say 4 and 5. Now these two conductors belongs to, let's say, another group because it is carrying a current of minus I. Now these two conductors are belongs to what different groups. Indirectly, this is a single phase transmission line. Now when you are calculating the GMD, okay, so or GMD equivalent, let me write like this. First of all, GMD of, let's say this is group A, this is group B, two groups. What is GMD of group A? Let me write here. GMD of group A means group A. So you have to write like this, always the distances. Not you have to write within the group, outside the group. Okay? D14, D14, just hold on. Yeah, D14, D15. With respect to conductor 1 we did. Now similarly, D24, D25, outside the group. I'm just giving an example. Then D34, now how many terms you are multiplying? Check. Total 1, 2, 3, 4, 5, 6 terms. So that's why it is what? 6th root. That's what GMD of group A. Now similarly, you need to calculate the GMD of group B. Again 6th root of. First you have to write with respect to conductor 4 all the terms. If I write with respect to conductor 4 all the terms, what I get? Check here. Just hold on. I need to increase the font size a little bit. Okay. Yeah. We get 6th root of D. We have to start with 4, na? D4 1, then D4 2, D4 3. Now with respect to conductor 5 you have to write D5 1, D5 1, D5 2 and D5 3. So again we are multiplying 6 terms. Now finally, what is GMD equivalent? The GMD equivalent is that, the GMD equivalent is that square root of GMD group A multiplied with what? GMD group B. Suppose if it is a 3-phase system, we get what? 3 groups like this. Okay, if it is a 3-phase system, we get what? 3 groups. GMD group A, GMD group B, GMD group C, but it's what? Cube root of GMD group A, GMD group B and GMD group C. That's how we can solve. Clear? Now, okay. Now, what is GMR? While calculating the GMR, you have to look for the conductors which belongs to what? Same group. So, what is GMR of group A? GMR of group A means what? GMD of group A. Let's see what is GMR of group A. While calculating the GMR, you have to look for what? Within the group. So you need to write here D11 in the group, D12, D13. Clear? With respect to conductor 1 we did. Now with respect to conductor 2, D21, D22 and what? D23. Now with respect to conductor 3, D31, D32, D33. How many terms you are multiplying here? 9 terms. So that's why it is what now? 9th root. 9th root. Okay? Clear? Now similarly, what is GMR of group B? What is GMR of group B? Here we have 2 conductors. Within the group you have to write. But D11 is what? D11 is R dash. D222 is R dash. D333 also R dash. You have to focus that. Here two conductors, D44 within the group, D45. With respect to 4 we did. Now with respect to 5, D54, D55. Fourth root, 4 terms you are multiplying. Now what is GMR equivalent? Square root of GMR of group A into group B. Okay. See, this is the simple procedure for calculation of GMD and GMR. We'll take an example so that you will get a clarity on this. For example, we have a single phase transmission line given like this. Single phase transmission line is shown below. Where the conductors here 1 and 2, this distance is given 5 meters, this distance is given 1 meter, let's say. These two conductors are carrying a current Y, these two conductors are carrying a current of minus I. Now, what is the inductance of single phase transmission line? Mu r value not given. And radius of all the conductors is 1 centimeter, means 0.01 meters. Now you need to calculate what is the inductance of single phase transmission line. Let's try this quickly. Let's try to solve this. Is the background is fine now? .29 Henry per kilometer. Okay, we'll see. See how to solve this, it's very simple. Yeah, first you need to calculate the GMD here, then GMR. What is GMD of group A? GMD of group A means what? Group A means we have two conductors here, 1 and 2. A group having 1 and 2. B group having a conductor 3, 4. Now GMD of group A means what? D13, D14 with respect to 1. With respect to 2, D23, D23. Yeah. Okay, and here what? Fourth root. So fourth root of D13. D13 is 5. D14 means what? This distance and this distance same. What is this? Under root of what? 25 plus 1, 26. Root over 5 square plus 1 square. Root right angle triangle, root 26. This is done with respect to 1. With respect to 2, what do you get? D23 and D24. D23 again what? Root 26. D24 is again 5 meters. So we get here the value 5.049 meters. Now you try GMD group A, group B also you will get same answer. GMD group B means what? Fourth root of, with respect to 3 and 4 you have to write D31 outside the group, D32, D41, D42. Now if you calculate this, again you get 5.049. Now what is GMD? Since GMD of group A and group B are same, we get the overall answer 5.049 meters only. Okay, now GMR means you have to go within the group. So GMR of group A, see, D11, D12 within the group, again D21, D22. Within the group only you have to write, again fourth root. 4 terms, fourth root. D11 is R dash. Into, what about D12? 1 meter. D12, this is 1 meter. And multiplied with D21, 1 meter. D22 means R dash. So we get here 0.088 meters. You calculate GMR of group B also, because they are what? Symmetry there exists between 1 and 2 and 3 and 4. That's why you get what? Same. You can try. If you have any confusion, you can try. Now what is L single phase formula? L single phase means what? L single phase means 0.2 ln GMD by GMR, millihenry per kilometer. This is a generalized formula in terms of GMD and GMR. If each phase having more than one conductor, we can use this formula. So what do you get now? 0.2 ln GMD equivalent 5.049, GMR equivalent 0.088. So if I solve this, we get 0.809 millihenry per kilometer. That is the final answer. Check it if you have any doubt. We'll go for performance of transmission line. That is the next chapter. Okay. Right. So what is performance of transmission line? Performance of transmission line means what? We are going to calculate the regulation and efficiency here. The line performance is calculated using performance of line calculated using two things. Number one, voltage regulation, percentage voltage regulation. Number two, percentage efficiency. See, percentage voltage regulation practically it should be within plus or minus 5%, and efficiency should be greater than what? 95%. This is for what? For better performance. For better performance, that is the story. This is for better performance. Okay. Ideal performance means voltage regulation should be 0, efficiency should be 100%. But practically that is not possible. But we can improve the performance using what? Some compensation techniques. Okay. So to do the calculations of performance, we have defined the transmission line as what? Short lines. Classification of lines. Short line, less than 80 km, medium transmission line, (80 km to 160 km), and the long transmission lines. Greater than 160 km. If it is a short line, out of 4 parameters now, we are considering only resistance and inductance. Okay. And medium line means what? We consider what? R, L and C. R, L consider here. But here what? R, L, C. Here all the 4 parameters you need to consider. Clear? Okay. But for calculations point of view, we do this calculations using what? ABCD parameters. Now we'll see what is ABCD parameters. So we replace the transmission line using simple ABCD parameters. Okay. But before that, what is the formula for regulation and efficiency? So regulation means what? I told you we are going to calculate the regulation and efficiency. The percentage voltage regulation is VR dash minus VR by VR into 100. We are just calculating only magnitudes. Okay, clear? These are all what? Phase voltages. Even you can substitute the line voltages also. VRL dash magnitude minus VRL by VRL. See, VRL is what? Full load voltages. VR, VRL. These are what? Full load voltages. For example, to understand this, let's say we have a transmission line represented with this box. This is the receiving end, this is the sending end. Sending end side source is connected. Sending end voltage Vs, sending end current Is. This is per phase equivalent circuit. Now, there is a load is connected here. This is what? Rated load. Rated load means what? Full load. If rated load is connected here, that will draw rated power. Now under this condition, the current is what now? IR here. The voltage is what? VR here. Now VR is the full load receiving end voltage. That's what we are talking. For example, let's say if it is mentioned a 132 kV 3 phase 100 MVA transmission line. Now this is the 132 kV which is a VRL. VRL is given in the problem directly. Then this 100 MVA means what? Rated apparent power at the receiving end. This is what? SR. Magnitude of receiving end power, SR. Clear? Now, tell me, what is VR? Magnitude of VR is what? Line voltage by root 3. Since for a transmission line, it's a star connection, line voltage and phase voltage is what? Phase voltage equal to line voltage by root 3. Okay, clear? And what is VRL dash? That is a no load receiving end voltage. No load means what? You have to remove the load. Load is removed. Source is still there for a transmission line. Then the voltage which is measured at the receiving end is what now? No load receiving end voltage. When the line is delivering the power to no load means what? Okay. The receiving end side, nothing is connected. Under this condition, whatever the voltage you see at the receiving end side, that is nothing but no load receiving end voltage. I hope this is clear for you. Okay. Now, VR dash and VRL dash. They are the magnitude of no load receiving end voltages. VRL dash means it's a line value. Okay, into 100 is there here also. No load voltages. no load receiving end voltages. That is a formula for regulation. And efficiency means what? Receiving end power by what? Sending end power. That's what the efficiency. Okay, clear? Now, let's see ABCD parameters. This is very important topic. ABCD parameters. Let's see. What are ABCD parameters? See, if I assume a transmission line is just a box, okay. Now this transmission line is replaced with its ABCD model. Clear? Now what is the relations here is Vs equal to AVR plus BIR. These are the ABCD parameter equations. Now if you see under no load, under no load means what? The load at the receiving end is removed. Now this voltage is what? VR dash. Now the formula for VR dash and IS is, if you substitute from 1, IR 0, na? So we can write Vs equal to AVR dash under no load. So VR dash equal to what? Vs by A. Now equation number 2, what is IS? C into VR dash. Now these two formulas are very, very important. Using this we calculate the no load receiving end voltage. Using this we calculate what? The charging current. IS is also called what? The charging current drawn by the line under no load. Okay, clear? Understand? So for any given transmission line, remember, for any given transmission line, we need to calculate what is A, what is B, and what is C, and what is D. For example, short line, if you see, what are the ABCD parameters? For short transmission line, this is what? The equivalent circuit. Short transmission line means between sending end and receiving end, we have just impedance. Where Z equal to what? R plus JXL. Clear? So we can write ABCD parameters are A equal to D equal to 1, B equal to Z, C equal to 0. In the matrix form, the ABCD parameters are, I am not going into the derivation, it is not required, ABCD. These are the ABCD parameters for short transmission line. But what is the condition for symmetry? A equal to D. What is the condition for reciprocity? AD minus BC equal to 1. Yes, it will satisfy symmetry and reciprocity. You can verify. You can cross verify that. Symmetry is satisfied here and even reciprocity also. Chalo. Clear? Now that's for short transmission line. Now when it comes to the medium transmission line means what? We have 4 networks. Nominal T model, the series impedance of is divided, and this is what shunt admittance. Z equal to what now? You know, R plus J XL. But Y equal to what? JBC omega into C. Based on this, its ABCD parameters are, directly I am writing one plus YZ by 2 here also symmetry and reciprocity are satisfied. That is for nominal T. Because the medium transmission line, the analysis is done using what? These 4 networks: nominal T network, nominal pi network, capacitance at load end network, and capacitance at source end network. All the 4 networks we are going to see now. Okay. So all right, now nominal pi model we'll see. This is what nominal pi model. Okay. Now ABCD parameters are what here? So this is for nominal pi model. Next, end condenser method or capacitance at load end network. Or end condenser method, both are same. The entire capacitance assumed to be at receiving end here. If that is the case, what are the ABCD parameters? In the matrix form, we can write like this. Next, capacitance at source and network or source condenser method. For this, if you see the equivalent circuit, the entire capacitance is assumed to be concentrated at the receiving end side. For this, if you write the ABCD parameters, this is what the capacitance of source and network model. Clear? I hope this is clear for you, right? So if you want to make a table for medium transmission line, let's see. This table will help you. Just have a look. We have networks like, we are writing here A, B, C, D, T network, pi network, capacitance at load end network, and capacitance at what? Source end network. With respect to that, if you write all the formulas, 1 plus yz by 2 here, A 1 plus yz by 2, so that the comparison becomes simple here. This is 1. Now parameter B, if you see, this is what here, z into 1 plus yz by 4. But this is just z. And this is y. All right. Now when it comes to the D parameter, so for long transmission line, if you see, okay, long transmission line. See this table quickly. Now long transmission line, which is very, very important, long transmission line. Here we are going to define small r, small l, small c and small g, small z, small y. Now L represents length of the transmission line. Small c means capacitance, because it's a distributed parameter model. That is the reason why we define like this. Before that, we can define small xl. Series reactance of transmission line per unit length. Small bc is nothing but what? You need to understand these things, then only the remaining things become what? Simple for you. Small z is nothing but small y is nothing but This is series impedance of transmission line per unit length. Ohms per meter. Small y, shunt susceptance of transmission line per unit length. Shunt admittance, I'm sorry. Mho per meter. Where L is the length of transmission line. Now, what I can write the capital Z, small z into what? L, capital Y. Okay. Now, apart from this, we are going to define gamma as a propagation constant. ZC is characteristic impedance. Just have a look of them. These things are what very, very important for proceeding further. Okay. Yeah. Gamma is the propagation constant. In this we can write real part is alpha, imaginary part is what? J beta. Units are what? Nepper per kilometer. Gamma is what? Propagation constant. This is nothing but what? Characteristic impedance. Units are ohms, and it is independent on length of the line. It is just independent on length of the line. Clear? Now, what are the ABCD parameters for long transmission line? The ABCD parameters are A equal to B, gamma L, cos H gamma L. They are the ABCD parameters for long line. Now, if you see equivalent T representation, equivalent T means what? For long line analysis, we use equivalent T. It's not Z, Z dash. It's not Y, Y dash. Nominal T, we have a Z, Y, but equivalent is used for long line analysis. So the Z dash can be written like this: Z into tan H gamma L by 2 by gamma L by 2. Y dash is what? Y into this is for equivalency and equivalent phi. Just the multiplication factors are reverse. Z dash equal to Z into what? So this is what equivalency representation and equivalent pi representation. Now if you see for lossless line, that is very, very important for us. If there is a question, means generally tested from what? Lossless line. Okay. All these things you already know, but just a quick review so that what? The problem solving become very simple for us. Okay. Now, if it is a lossless line, this is very, very important. For lossless line, if you see, what is lossless line? When the losses in the line is 0. Losses in the line is 0 if resistance is 0 and conductance is 0. If that is the case, gamma is what now? Simply we get J beta. There is no concept of what? Resistance and what? Conductance now. And a characteristic impedance ZC, we can write what? Root over J XL by what? JBC. That means JJ get cancelled. XL by BC. If you multiply with, see, XL means omega L. This is also called surge impedance. For lossless line, characteristic impedance is called what? Surge impedance. The typical value of surge impedance is what? 400 ohms for transmission lines and 40 ohms for what? Underground cables. Okay? You already know these things. And now, yeah, what are the ABCD parameters? A equal to D cos beta L and parameter B sin beta L. But remember, parameter A phase angle is what? 0 degrees. Parameter D phase angle is what? 0 degrees. Parameter C phase angle 90. Parameter B phase angle also 90 degrees for lossless line. For lossless line, always this is true. And lossless line, these things are very, very important. Now, what is the typical value of ZS? ZS equal to 400 ohms. Overhead transmission line. 40 ohms for underground cable. It is independent on the length of the line again. Not depends on the length, independent on the length. Now, what is the typical value of beta? Typical value of beta is what? 0.06 degree per watt kilometer. Otherwise, 1.047 into 10 power minus 3 radians per kilometer. See, beta we can calculate. How to calculate beta? That's what gamma. And beta is what now? Root over what? Beta formula is this. Small xl into small bc. Otherwise, omega into small l into small c. If the values are given, otherwise what? Not given, you take it what? Typical value. For example, I will give a question here. If it is mentioned like this, calculate ABCD parameters. Lossless 400-kilometer long transmission line. Nothing is mentioned. Just calculate the ABCD parameters of a lossless 400-kilometer long transmission line. So how to solve this? Very simple. So length is given 400 kilometers. Since inductance, capacitance not given, XL and BC not given. So what is we assume? Typical value of beta is what? 0.06 degree per kilometer. What is beta L? Beta L 0.06 into 400, which is 24 degrees. Now tell me, what is parameter A equal to D? Lossless line, cos beta L, cos 24 degrees. Okay, just tell me this value, cos 24. You get 0.9135. B equal to what? ZS is not given, so take it what? 400 ohms. This is C, not B. Parameter C means admittance. These are the ABCD parameters. A simple question. Now, how to calculate the regulation and efficiency once I know the ABCD parameters? Okay, to calculate the regulation and efficiency, because you remember our objective is what? Calculation of regulation and efficiency, right? Okay, because we have to find out the performance of the line. Performance of the line means what? Calculation of regulation and efficiency. So to calculate the regulation and efficiency, we have a simple procedure. So what is the procedure here? So first we need to calculate the ABCD parameters. That is what the step 1. See, once we find out the ABCD parameters, the next step is we have to calculate VR and IR. How to calculate VR and IR? From the line data, if you see, generally we take the receiving end voltage, full load receiving end voltage, VR means. That is our reference. So the line voltage magnitude is given to you in the problem. Divide with root 3 and phase angle is what? 0 degrees. But how to calculate IR? Magnitude of SR. SR is given, otherwise PR is given to you at an angle cos inverse of power factor of the receiving end. Clear? Yes. Suppose if PR is given in the problem, receiving end power, theta is the receiving end power factor angle. PFR means receiving end power factor. Even you can define like this, SR is a complex power. If you do like this, real part is the active power, imaginary part is what? Reactive power. If we calculate the magnitude, magnitude is the complex power and phase angle is what? Theta. Plus for leading, minus for lagging. So this is a procedure, but this is a complex procedure because see, you need a complex mode operation of calculator to solve this. Yes. Now let's see. The next step is that calculate Vs and Is. So Vs formula is what? Now step 4. In the real part is active power, imaginary part is what? Reactive power. Theta S is the sending end power factor angle, theta R is what? Receiving end power factor angle. Now, after that, regulation and efficiency. What is the formula for regulation? You are ready with what now? All the things. Take magnitude. Efficiency means you are already calculated PR and PS. Yes, that's it. Check it here if you have any doubt. You already calculated PS, you already calculated PR. Then you can calculate the regulation and efficiency easily. So we'll solve some gate questions so you'll get a clarity on this. See this question and try to answer. Now, so to solve this question, it's very simple. What is mentioned here? See, the line is what? Delivering 50 megawatt power at 0.9 power factor lagging power factor. See, what is the data given? It's basically 220 kV transmission line. Yes or not? It's a 220 kV transmission line. It's clearly mentioned. So VRL given here, magnitude. Now what is VR? Okay, then the line is delivering 50 megawatt at 220 kV with a power factor of 0.9 lagging. So what is PR given? 50 megawatt active power at the receiving end. So what is the power factor of the receiving end? PFR? Nothing but cos theta R, that is 0.9. From this, what is theta R? Cos inverse 0.9. 25.842 degrees. Chalo, theta R we know. Now, what is IR? Because we need to calculate IR, then only we can calculate the sending end voltage. Is asking what is the magnitude of the line value of sending end voltage. VS is asking. So since VS is asking, first we have to calculate what is VR, then we can use VS equal to AVR plus BIR formula. So PR by minus, why minus? Because it's a lagging power factor, clearly mentioned. So if I substitute this, minus 25.842. Already we done that. So if I solve this, what I get? $145 amperes. Okay. Now the formula for Vs equal to simple. When you are multiplying the complex numbers, multiplication must be done in what? Polar form, and addition will be done in what? Rectangular form. C is mentioned, A and D, B parameter. AV are A 0.936 at an angle 0.98, right? Into 220 kV, so 220 by at an angle 0 degrees. B 142 point, okay, 0, 76.4 degrees. This is multiplied with IR. Now tell me, when you are doing the multiplication, no, magnitudes will be what? Directly multiplied, phase angles will be added here. 0.936 into 220 by root 3 into 10 power 3. 220 by root 3. This is how we have to do. There is no other way. So we get 118,887.9674. Okay, 0.967 at an angle 0.98. Magnitudes are multiplied, phase angles are added. 0.98. That is the first part. And the second part is what? This one. These two magnitudes you multiply. 142 into 145.79. Because in GATE, the complex kind of calculations you can't done directly. You have to convert from polar to rectangular, rectangular to polar like this. How? Have a look. 2070.2.18 at an angle. What? 76.4 minus 25.84. So we get 50.56. Okay, these many volts. Now if you done this, then again you convert this into what? Rectangular form. How to convert this into rectangular form? Magnitude cos real part plus j times magnitude sine of this angle. Similarly here also. If I solve this, final answer I am going to give you now. 18887.967. So we get final answer 133.246 at an angle 7.773 kV. But this is what? Magnitude of the sending end voltage, phase voltage. So we got Vs, phase voltage. How much? 133.246. but he is asking magnitude of the line voltage root 3 into Vs. If I do so, $230.789 kV. That is the answer. So option is what? See, 230.78. See, this is how we need to solve. This is a one kind of question which is commonly asked in the GATE exam from our performance of transmission lines. Okay, we'll go for next question. This is a simple and straightforward question. Let's see what is given in the question. Read the question carefully. You'll get the answer easily. So let's see in the question what is given. ABCD parameters are given. It's clearly mentioned which is a 220 kV transmission line. Means VRL is what? 220 kV. Since it's a 220 kV line, VRL given 220 kV. ABCD parameters given. If the sending end voltage of the line for a given load delivered at nominal voltage of 240 kV, sending end voltage of the line for a given load delivered is a nominal voltage of what? 240 kV as mentioned. Now, what is the voltage regulation? See, we need voltage regulation means what? The formula directly, shall I write now? VSL by what? A. Hundred. What is VSL? 220 by 0.94. Sorry, 240 by 0.94. Minus if you solve this, you'll get approximately 16%. It's a direct question. Now, let's see the another question. For example, if it is mentioned like this, okay. A 3-phase 58 400 kV transmission line 300 km long. The line inductance is 1 millihenry per kilometer per phase and the capacitance is 0.01 microfarad per kilometer per phase. The line is under open circuit condition at the receiving end and energized with 400 kV at the sending end. So sending end voltage is what? Given. The line is operating under open circuit condition. sending end voltage given, inductance is given, capacitance is given, small l and small c. What is that? 1 millihenry per kilometer per phase. Okay, 0.01 microfarad per kilometer. Not mention R and G. So that means what? It is a lossless line because not mentioned R and G. So that is the first conclusion, not mention R and G. So what is asking? Calculate the receiving end line voltage in kV. Round off to 2 decimal places. That means receiving end line voltage means what? VRL dash is asking. Why VRL dash I am saying? Because the line is operating under open circuit. Line is operating under open circuit condition means what? No load. Okay. He is asking VRL dash is how much? But we know the formula for VRL dash. What is the VRL dash? VSL by A. Since it is a long line, what is the formula for A? A equal to cos beta L. But beta not given means you can take typical value, but beta indirectly given in L and C. So you have to calculate the beta. Omega into root over what? Small l into small c. Both are given per kilometer. So that's why you substitute here now. We get the answer easily. Yes or not? What is omega? 2 pi into 50. L and C, 1 millihenry. C, so what is this value? Check it. We get 9.9345 into 10 power minus 4 radians per kilometer. Because L and C I am substituting per kilometers. Okay now? In degree per kilometer, so you need to multiply with 180 and divide with pi. So we get 0.0569 to degree per kilometer. If that is the case, what is A? A equal to cos beta L. Let's substitute cos of beta. L is what? Length of the line given 300 kilometers. If I solve this, we get 0.9559. Now what is VRL dash? What is VSL given? 400 kV. We get 418.44. So that's the final answer. 418.44. Okay, so we'll go to the next question. Yeah. See this question. For a 400 kilometer transmission line, the series impedance is given. It's a lossless line because resistance is 0, conductance also 0. Okay. So anyway, I will write the series impedance first. So what is the series impedance given here? Z equal to what? J 0.5 ohms per kilometer. Indirectly, small xl is given 0.5 ohms per kilometer. Fine. What about small y given? J5 into 10 power minus 6 micromole. So mole per kilometer indirectly. That means BC also given. What is asking? The magnitude of the series impedance in ohms of the equivalent pi circuit. For equivalent pi circuit, what is Z dash? Z into what? Sin gamma L, sin H gamma L by gamma L. For lossless line, alpha 0, so we get simply Z equal Z into sin beta L by beta L. Lossless line. So the objective is here to calculate the beta and beta L. So what is beta? Root over small xl into what? Small bc also we can write. What is that? You substitute that. If I substitute, small xl is how much? 0.5. Small bc, 5 into 10 power minus 6 no? So you get radians per kilometers now. In degree per kilometer, (0.0905). Beta L is what? Length of the line is what? 400 kilometers. 36.237 degrees. Otherwise in radians, .6324 radians. Okay. Now tell me, what is Z dash? Z dash is what now? Z is what? J 0.5. into sine beta L but in the denominator you should substitute beta L in radians, otherwise you will end up with wrong answer. So the answer is J.46. So magnitude is asking, the answer is what? Magnitude means J will not come. 0.46732, approximately 0.467. So that is how you need to calculate. Okay. Acha, okay, previous question only it is showing, right? Chalo, actually we discussed these two questions, right? After that, this is the question we discussed. After this question we discuss. Look, this question, inductance and capacitance is given and asking to calculate the line is operating under no load. What is VRL dash? Check the question once. Since VSL is given, okay, okay, now is it clear now? Yeah, see in this question, the line is operating under no load mentioned, it's a 400 kV line given, okay. Now is asking to calculate, what is a no load receiving end voltage? VRL dash. So VRL dash means what? VSL by A only. So let's see, we just calculated how A equal to cos beta L, beta we calculated. Then after that what? We are just calculated, VRL dash using the formula VSL by A. I hope this is clear. Now, the next part of the question you see, this question we discussed. Again, it's a lossless line, inductance and capacitance is given. Now, this question we discussed now. For a 400 kilometer long transmission line given, series impedance and shunt admittance given, the magnitude of the series impedance in ohms of equivalent pi, what is the formula for Z dash? Z into, sin h gamma L by gamma L Yes or not? Z into sin h gamma L by gamma L. So for a lossless line we can write gamma can be replaced with j beta, so that we can write sin beta L by beta L for lossless line. So again you have to calculate beta in this question. Beta equal to what? Either you can use omega into root over L into C, or what? Root over XL into BC, right? We just calculated beta and beta L. But careful, while substituting sign of something, it should be degrees, or you are multiplying that with what? Angle, or dividing with angle means that angle must be in what? Radians. Okay. So now we got the answer as Z dash equal to this, but he's asking only magnitude. The value of that will be 0.46732. It's not 0.5, it's a 0.46732. Okay. Clear? I hope this is clear for you. Just have a look of that. Whether you got some clarity or not. Have a look, please. I hope this is clear for you, right? Now we'll go for the another important concept called power flow equations. So power flow equations in terms of ABCD parameters. So we'll see power flow equations in terms of ABCD parameters. So we are interested about, for a given transmission line, what is the power delivered at the receiving end? We are going to calculate here, PR and QR, in terms of ABCD parameters. The formulas are like this. Okay, but before that, the parameter A having a magnitude, phase angle is small a, small b. So the formula for PR is what? VSL, sending end voltage magnitude, B minus delta, where delta is the load angle. This is the formula for PR. So this is what power flow equations in terms of ABCD parameters. Clear? right? Now, what is the condition for PR max? PR max means maximum active power delivered to the load. Okay, the condition is what? Load angle equal to parameter B phase angle. If that is the case, what is PR max you get? We get VSL VRL by B cos 0 1, as it is this will be. Under this condition, what is QR? First part of the B minus delta is 0, so we get only second part. So this is negative, means what? Line is not delivering reactive power to the load, line is expecting reactive power from the load. That means when delivering maximum active power to the load, QR negative means what? Load has to supply the reactive power. Load cannot supply the reactive power because 85% of the loads are induction motors. They need reactive power. But to achieve PR max, QR must be negative means, yes, it is possible by using the shunt capacitive compensation at the receiving end. Okay. So to achieve this condition, the transmission line require shunt capacitive compensation at receiving end, because QR negative means line is expecting reactive power from the load, but load cannot deliver the reactive power because 85% of the loads are what? Induction motors practically. So we need a shunt capacitive compensation to achieve what? PR max. That is what the first important thing here. But compared to this, approximations are very important for us. Okay, let's go to the approximate model. Approximate means what? Short line approximation first. Short transmission line means between the sending end and receiving end we have only Z. What is this Z? R plus JXL. We can write mod Z at an angle what? Theta. Theta is what? Tan inverse XL by R. Okay. Now if you see the impedance triangle, now the formulas for PR and QR, you see, there is no concept of A. A is 1 here for short line. Okay, what is the condition for PR max? What is QR under this condition? That's it, simple. Okay. Now if you see the last one, if resistance is what? 0, for example, if you have a transmission line with resistance also 0, means the formula for PR is what? VSL VRL by XL sin delta. QR is what is the condition for PR max here? PR max is now these formulas are very, very important. Clear? Now, if you do the analysis like if you have a 2 buses, in between we have a transmission line. Bus 1 voltage V1 delta 1, bus 2 voltage V2 delta 2. If that is the case, the power here and power here is what? Same, P1, P2. Why? Because there is no loss in the line. It's a lossless line. V1 V2 by XL sine of delta 1 minus delta 2. Q1 we have a different formula and Q2 we have a different formula. These formulas you should be very, very careful while solving the problems. And what about reactive power loss in the line? Remember, active power is always flowing from what? Higher load angle bus to lower load angle bus. But reactive power is always flowing from what? High magnitude voltage bus to low magnitude voltage bus. Okay, that's how active and reactive power will flow generally in transmission line. Active power is what? Always from higher load angle bus to lower load angle bus. But reactive power is always high magnitude voltage bus to low magnitude voltage bus. I hope this is clear for you. So we will see now some numerical questions on this topic. Now we'll see one gate question here. Okay, a 50H 275 kV transmission line is given here. Okay, have a look at that question once. A 50H 275 kV length of the line, 400 km, has the following parameters. Resistance, inductance, capacitance is given. The line is represented with nominal pi model. The moment he has mentioned nominal pi model, you should notice what are the ABCD parameters of nominal pi model. You know what is the ABCD parameters of nominal pi model now? Yes or not? Again the same problem. Yeah. What about the ABCD parameters of long line? For long line, the ABCD parameters are what? Sorry, nominal pi model, what are the ABCD parameters? A you know, B you know, B equal to Z, A equal to 1 plus YZ by 2. Okay, but what is the question actually? In the question is asking to calculate, see the question clearly. The line is represented by the nominal pi with the magnitude of the sending end and receiving end voltages are given. The phase angle difference between Vs and Vr. What is the phase angle difference between Vs and Vr according to us? Delta. But he has mentioned theta here. Okay, let it be. For maximum possible active power transfer to the receiving end in degrees is round off to 2 decimal point. It's a very simple question. The phase angle difference between the Vs and Vr means what? He's talking about what? What is delta for maximum power transfer? For maximum power transfer, delta equal to what? B, where B is the parameter B phase angle. What is parameter B? That is Z. In this, magnitude is what? Mod B, phase angle is what? B. Otherwise, what is this Z? Z equal to what? R plus J XL or omega L. Let's see, R is given 0.035 ohms. Okay. Per kilometer given, okay, let it be. Even you can calculate in ohms also, not a problem. But inductance, omega means what? 2 pi into 50. L is given how much? 1 millihenry, 1 into 10 power minus 3. Okay. So what is this? Okay, into what? Length you multiply. So that is not going to affect the phase angle. Okay. So anyway, if you want, you can multiply with what? 400 kilometers. So that what? You get, you know, the capital Z. Okay. Now try to find out this Z value first. 0.035 into 400 will get 14 plus J times 125.663 ohms. Now what is this B? Parameter B phase angle, tan inverse of what? 125.663 divided with what? 14. We get 83.64. So that is what? So the load angle difference between the buses to get what? Maximum possible power transfer. The condition for PR max. This is a question based on condition for PR max, and also he has mentioned nominal pi model. For nominal pi model, B equal to Z. If you know this, then the calculation part is very, very simple. Okay, have a look of that. Now we'll solve another question. Let's read this question, get some clarity on the question. Okay, I hope you got the answer. Some of you able to solve. Okay, let's see how to approach for this question. It's very simple. Load angle is not given here. Have a look. Load angle is not given. But what I say, the V1 magnitude, V2 magnitude is given. So first you write the active power balance. This kind of questions you need to write the active power. Everywhere active power is what? Known. So if you write active power, yeah. Wait. Active power coming from generator 1 is mentioned. Active power going here also given. That is 15, 20. Now this power, active power is what? P1 here. 20 minus 15 is what? 5. If that is the case, this side also P2, which should be what? 5. Again, if you want, cross verify. What is given here? 20. Then from here what? 15 should come. Yes, 15 given. Everything is given. So using this P1 and P2, you calculate delta. Sin delta formula na. XL is given how much? 0.1 per unit. What is asking here? QG1, QG2 and Q loss respectively. Okay. We can do it. It's not a big deal. So from here what I can write, P1 equal to P2 equal to 5. That is, we evaluated. 20 minus 15 is what? 15, right? Okay. 5 equal to 1 into 1 by 0.2, sorry 0.1 sin delta. Sin delta equal to 0.5 means delta equal to 30 degrees. That is the first conclusion. Later you write the reactive power balance. Reactive power only you write. Reactive power means what? Here QG1, we don't know. This is Q1, we don't know. But demand is given. How much? 5. Here. Imaginary part is reactive power. This is what? Q2. This is QG2. That also not known. Now what is the reactive power here? Taken 10. So we can calculate Q1 and Q2 now. We have a formula for Q1 now. What is the formula for Q1? V1 square by XL minus V1 V2 by XL into cos delta. Let's substitute 1 square by 0.1 minus 1 into 1 by 0.1 into cos 30. Yes, let's calculate this. So what is the answer you get? we get 1.339 per unit because all the things are given in per unit. Now what is the formula for Q2? V1 V2 by XL cos delta minus V2 square by XL. If I substitute this, we get minus 1.339 per unit. Minus means what? Actually, line is what not delivering, it is what taking. So what is Q loss? Q1 minus Q2. 1.339 only, okay. Approximately 1.34 per unit. So we substitute here 1.34 minus of minus 1.34, 2.68. Now how to calculate QG1? So here you see QG1 equal to what? Q1 plus 5. Incoming equal to outgoing, na? What is Q1? 5 plus what? 1.34, 6.34. Okay, 6.34 fine, 2.68 fine. So the only option is this. That's it. Okay, if you want QGT also you can calculate like this. QG2 plus Q2. Incoming equal to outgoing equal to 10. So what is QG2? 10 minus Q2. 10 of minus 1.34. So 11.34 per unit. I hope you understand. See, this is how we can calculate for a given problem. First we have written active power balance separately and reactive power balance separately. If the questions are given, you have to do like this only. So we have one more GATE question. We will see that so that you will get more clarity on this. Yeah. See this question. Bus 1 with voltage magnitude V1 1.1 per unit is sending reactive power Q12 towards bus 2 with the voltage magnitude V2 also given 1 per unit. Lossless transmission line have reactance X. Keeping the bus 2 voltage fixed at 1 per unit, the magnitude of the voltage at bus 1 is changed so that the reactive power Q12 sent from bus 1 is increased by 20%. The real power flow through the line under both the conditions is 0. Acha, both the conditions real power is 0. Clear? That means what? In the case 1 and what? Case 2, right? Chalo. Then the new value of the voltage magnitude V1 in per unit round up to 2 decimal places at bus 1 is. How to calculate here? Real power 0 means what? What is the load angle? See, in between the two buses, we have just reactance. That's it. Reactance of the line only. Right. This is what? V1 at an angle delta. V2 angle 0, for example. V1, V2 by X sin delta. That is equal to 0. Means delta is 0. But what is the formula for Q12? Q12 means what this? Sending end. Sending end means what? V1 square by XL minus V1 V2 by X cos delta. Delta anyway 0. That's why the formula is what? V1 square by X minus V1 V2 by X cos delta. Cos 0 1. This is what the formula for Q12. Yes or not? Chalo. Again I am reading the question. The sending and reactive power Q12 towards bus 2 with voltage magnitude 1 per unit through a lossless transmission line of reactance X. Keeping the voltage at bus 2 is at 1 per unit. The magnitude of the voltage at bus 1 is changed so that the reactive power Q12 sent from bus 1 to increased by 20%. We don't know what is the value of X. But now the voltage is increased by 20%. Okay. Q12 is what? Some, okay, this is what this. Q12 dash is what? Okay, Q12 will say initially. V1 is what now? 1.1 square by x minus 1.1 into 1 by x. This is what initially. Okay, clear? Now, what is Q12 dash? I don't know what is V1. V1 square by x minus V1 by x. Yes, V1 square by x minus V1 by x, because V2 is what? 1. V2 is 1. Now what is this Q12 dash? Increased by 20%, means what? 1.2 times the Q12. So what you can write now? V1 square by x minus V1 by x equal to 1.2 times what? 1.1 square by x minus 1.1 by x. Right? This implies we'll get a quadratic equation. Just check it. X you can cancel on the both side. So what do you get? 1.1 square means 1.21. 1.21 minus 1.1. So we get a V1 square minus V1 minus 1.21 minus 1. What do you get? Minus 1.1, I'm sorry, into 1.2 again, 1.132, sorry. We get a quadratic equation. You solve this quadratic equation, you will get what? The new value of V1. Okay. Q12 is the previous case. Q12 dash is the present case. Q12 dash is what? 1.2 times the Q12. Okay. So if I solve this, we get two values for V1, 1.118 and minus 0.118. So the best answer is what? A. This one, 1.118, because it cannot be negative, right? Okay. The answer is what? 1.118. This question is given in GATE 2020. Very simple question. Nothing great. Okay, so that's about performance of transmission lines. Okay, and I will end the session here. So the next session, most probably I will discuss in the discuss tomorrow morning. Okay, but that will be intimated to you. Don't worry. So in the next session, we are going to see the analysis part, right? And even power factor correction and voltage control also we are going to see in the next session. So that's it. Thank you. Thank you for watching and all the best.